Okay, good morning. So I hope that you are doing well. We continue the lesson. We ended up yesterday with cyclic groups. It's not complete. Let us complete it. But let us, for warm up, do this example, which we'll need for the next theorem. Yeah, it's good to remember this as well. But I prefer to put it as an example rather than a theorem. So let m not equal to 0 and n be integers such that m divides n, meaning n is divisible by n. Show that the subgroup generated by a to the n is a subset of the subgroup generated by a to the m. Of course, when I say a subset, because we know that the left-hand side and the right-hand side are already groups, subgroups, so the left side is also a subgroup of the right side. Yeah. But here, I just want to show that this is the inclusion that works. Okay. And of course, I am a little bit sloppy in my notation. So it means that we have a group G. I have picked A from G, and then I am making this subgroup generated by A to the n and things like that. Okay, so how should we prove that? So in principle, what we know is that m divides n. My goal is to show that A, the subgroup generated by A to the right-hand side, is a subset of the subgroup generated by A to the left-hand side. Yes, this is what we want to show. Okay, so do you remember we learned yesterday the question, the strategy you should have, you would say that the left side is a set because of this symbol. The symbol only makes sense if the left and right are sets. And I want to prove the left side set is included in the right set. And there is a trick, there's a very standard way to do that. You pick one element, any arbitrary element from the left one, and try to show that the one you picked is guaranteed to be in the right side as well. That's the meaning of being subset. Yes? So let us do it together. So I would say let x belongs to A to the n. In the exam, you don't need to explain, but if you want to write notes, it's good to see. We show that. Can you fill it up for me? We show that what? X belongs to A to the n. Yes, this is what we want to show. This you don't need to write in the exam, but it is good for writing notes. When you read it, you can see it later. So x belongs to A to the n. Then you need to remember what this symbol means. So I would say definition of this symbol. So can you feel it? What is the meaning? X belongs to this. It means there exists some integer k in Z such that x is equal to A to the n to the power of, that's the meaning, yes? Do you remember that? So when I say, yesterday we learned this, yes? We learned that the definition, so let me put a box here, whatever this box is, it's a group element. The definition was whatever inside the box to some power k, such that k belongs to Z. So that was more or less the definition we had yesterday. Okay, but the box here is this guy. Yes, that's the same. Okay, but then what happens? This means that x is equal to n to power nk for some k in Z. Okay, so that is the definition takes me up to this point. But if you look what you want to do, you want to show that x belongs to this, and it means somehow m should be involved in your problem. So far, I don't have m involved. N was the one given from the beginning, and k is something comes out from the definition. But it has not connected to A to the mth yet. And that is understandable because still I haven't used this assumption. Okay, so what is the meaning of this assumption? So m divides n means what? So you need to remember again the definition. It means n is divisible by m. So it means there is a q in Z such that the right hand side is m times q. Understandable? That's the meaning of divisibility. Okay, and then if I give this number 1 and I give this number 2, so from 1 and 2 what I can conclude is x is equal to a. Instead of n, I put mq. And then I have k. Okay, what is the last step? Can you help me? Because I hope that you remember what we're supposed to do. We want to show that x belongs to a to the mth. I have to convince myself that x is a power of a to the mth. Is that right? So what should I write?
A to the power of m to the power of
qk. Yes? And this is guaranteed that this belongs to z. Do you agree? Because q belongs to z, k belongs to z, so the product belongs to z. So that's it. X is an integer power of a to the m. So this means by definition, x belongs to this argument. So you see, it's a very good practice to learn how to write, but that's extremely easy problem in algebra. Any questions? Understandable? Okay. So let us go to the fundamental theorem of cyclic groups. Okay? It's a big name, but it's very hard. But this is a very good, it's a very real theorem for abstract algebra. So every subgroup of a cyclic group is cyclic. Yes? Understandable? So it means that if you have a group which is cyclic, and if you somehow come up with a subgroup of it, that subgroup is still cyclic. Yes? So in order to understand the theorem, I want you to define for me, do you remember? Because these are important. That's why I just emphasize on the role of memory. If you have forgotten about what was the meaning of the cyclic group, there is no way to understand how to prove this. So I want some of you define for me what was a cyclic group we defined yesterday. A group G, I'm just recap. A group G is called cyclic. Cyclic is what? If? Yes, please.
If there is an element in G.
So there exists an A in G such that.
Acts as a generator and.
So what's the meaning of being generated? G becomes equal to the group generated by this element. That's the meaning of, thank you. That's the meaning of a group being cyclic. It means that if you look inside the set, inside the group, you can find an element so that when you construct this in this form, this becomes the whole set. Is that understandable? That's the meaning of being cyclic. Okay. Now we want to go to the theorem 1. So here what I have, I know that G is cyclic. So G is cyclic. I know that H is a subgroup. Do you remember this symbol? H is a subgroup of G. My goal is to show that H is cyclic. Okay? So if you want to think about the problem, to prove H is cyclic, you have to find a generator for H. And that's not that easy, so you have to get used to this way. I'm not expecting you be able to understand, to be able to do the proof yourself. But these are the techniques that you have to develop when you're learning abstract algebra. Okay? So, let us translate it one by one. I have two assumptions. I have G is cyclic, and I have H, which is a subgroup of G. My goal is to show that H is cyclic. I know the goal. My goal is to find a generator for H. Yes? Okay. But let us translate this. Exactly, you see it on the board. When you tell me, G is cyclic, exactly definition. What does it mean? It means that there exists A in G such that G is equal to this. I did nothing, I just write the definition. Okay? But the point is that if you want to succeed to prove this theorem, the only thing you have, because you see this is very abstract, nothing is there. So when it is cyclic, I bring A in so that it generates G. So somehow, if I want to prove that H is cyclic, I have to find a generator for H. But do you feel that this generator somehow should be related to the generator of the whole set? Because there is nothing in my hand. The only thing I have available, if this is going to be done, I have to use this A somehow to make a generator for H. Because this is the only thing I have. Okay? Okay, so if I want to give you a feeling, so first of all, there is one case that is already done. I mean, you don't need to prove anything. Because one of the cases that H can be a subgroup of G is that H contains only the identity element. Yes? So if H is only this subgroup, do you agree this subgroup is cyclic? It is cyclic. What is the generator of this subgroup? E itself. So if H is this case, we are already done. So in principle, you should write that. If H is this subgroup, it is generated by E, and we are done. Okay? So we assume that H has something more into it. It has E, it should have E in it, but it has something more to it. Okay? So this is why from now on, imagine that H has at least two elements. Okay, so let me write it. If H is this, since H becomes this, we are done. Yes? So let us say that, for example, there exists an H such that H belongs to H, and this symbol means and, H is not E. Because if it includes only E, we are done. So the interesting case is the case that there are some element within H which is not E. Then I want to show, yes, still it is cyclic. Okay, so let me start from here. So you see, let me give you a picture. So this is G. H is a subgroup, is somewhere here. There is an A here. This A is responsible to generate G, okay? But it might not be inside here. My goal is to find a generator for H. So do you get a feeling what will be the generator of H? Of course, you have to be experienced a little bit. So you see, A is not here, because if A is already there, we are done, yes? So if A is outside, A to power 2, where is A to power 2? It's definitely in G. But it might be inside H, we don't know. If A2 is not inside H, let us consider A to power 3. A to power 3 is definitely in G, okay? But it might not be in H. So you start increasing this power, somehow it will jump into H the first time. My goal is to show you that the first time that A to some power enters H, that will play the role of the generator of H. Okay? I'm not saying it's obvious, but this is my strategy. I want you to have the line of thought. Okay, is that clear? Okay. But when I say H belongs to H, so you see here, H belongs to H, and H is not equal to E. So if H belongs to H is somewhere here, it's automatically in G. because H is a subset of G, or subgroup, it doesn't matter here, H belongs to G. And if H belongs to G, because G is this, I can write there exists an N in Z such that H is equal to A to power N. Do you agree? Okay, but now because of this assumption that H is not E, I can say a little bit better. I can say belongs to the set of this. Do you agree? Because if H belongs to this one, I cannot rule 0 out, but here I can rule it out because I know that H is not E. If N is 0, H will be E, but I'm excluding E. So that is not wrong, what I have written. Is that right? Okay. But even I can do better. Do you think I can take this out and write it, there exists an N in N? Can I?
Yes.
Why?
Because it's a cyclic group, right? So then it's just.
No, we don't know yet. We don't know H is cyclic.
Oh, but
So we know
G
that
is- but G
H,
is cyclic.
A to power N, is here.
Yeah, but
If
I mean,
in the beginning you are lucky and N is positive, what I have written is correct.
yeah, no, but I mean, since G is cyclic, then A to power N also wasn't that the definition of cyclic, that you could do it with only natural number
No, no, no.
exponents?
No, no.
There was
If
something
it
we
was,
talked about
yeah, it was.
yesterday with
Yeah,
the-
you have to remember correctly.
Yeah.
It was only for the finite case.
The finite case.
Yeah,
Okay,
that's
sorry.
not the case.
Okay, yeah, then
Yes?
then I don't know.
No, but then you know. That's what I'm saying. You see, do you agree? From here, first I have to write this if I want to respect the definition. But here I want to say I can say more. The first thing I want to say more is that I am excluding 0. Why is that correct? Because I know H is not E. So this means 0 is excluded. But I want to even say more. I want to say that this is natural indeed. There exists a natural number. And I am telling you that if this number from the beginning is positive, so it is automatically natural and I am done. But what happens if this particular N that I chose and write H is negative? Then what happens?
In practice, it's taking the inverse that many times instead.
Yes, and where the inverse is?
It's also in the group.
In the H,
Yeah.
because H is already a subgroup. So that's why I can write this. Okay, is that right? Okay. But you have to you have to justify this. Understandable, everyone? Is that understandable? Okay. So now my question is that I define a set for you so that it is the m's in N such that A to power M belongs to H. Okay, so if you don't mind, let me go one step forward here and write there exists, H is a subgroup. So this means there exists an N in N such that H is A to power N. Okay, now my question for you is that I want you to improve your skills in reading the text, the mathematical symbols. First of all, read this set and I am asking you, this set is a subset of a famous set. What is that set? You have to be very good in reading these things. So my question is that I am defining, semicolon equals to, it means I am defining this for you. For the time being, consider it out of the blue, okay? But you will see why. But here, I am telling you that A is a subset of a famous set. Can you fill up the question mark for me by reading this? So this is something you have to practice and be very good at it, okay? So how do you read it in English? The set A consists of all elements from the natural numbers, but not all of them, the ones for which A to the M belongs to H. So what are these? What are these? What are the nature of the things inside this A? They are numbers from n. So this means that this, forget about how it is defined, this is definitely a subset of n. Do you agree? It's a subset of n. But I am claiming that, can it be empty? Can it be empty? Do you think that this set, because sometimes a set can be empty, but do you think that in this case A is empty? Why not? Yes?
Because if it's empty, then we don't have the identity in H.
No, it doesn't have, it has nothing to do with that one, because A is a set of numbers. It has nothing to do with the group that you started from. Do you understand that? So, but this set, can it be empty? Okay, think a little bit, 30 seconds. Okay, so let us give you a little bit of feeling. So, if I want to understand A, what A is, you have a set N, which is 1, 2, 3, etc. Okay? So what you do, you pick one from N, raise A to power 1, it becomes A. If A is in H, you put 1 there. If A is not in H, you exclude 1. Then you go to 2. You pick 2 from N and determine A to power 2. If A to power 2 happens to be in H, you put 2 inside this bag. If not, you throw it out. Is that understandable?
Yes.
So my question is that, do you think all of these elements will be thrown out?
No.
If the answer is yes, this becomes empty. Do you see that? If the answer is no, it is not empty. My claim is that the answer is no, but I want to tell you to tell me why.
Because H
Yes?
is non-empty.
It's because you have G, right? And A generates G.
No.
And also
No.
No?
No. Yes?
Because without H is not empty.
No. So these are very important. If you cannot fix these things, this is why abstract algebra becomes formidable. Yes?
Because if
No, I want the name. I want the name of the number here. It is on the board. Okay. So why I did that, yes? There exists an n in n so that a n becomes h and h is from h.
Okay.
So you shouldn't look for a particular number, 5, 6, who knows? But the existence of such a natural number by this was proved for you, yes? So it means that this cannot be empty because at least this n is there. Do you see why this n is there? Because a to power n is h. Where was h? H was in H. So it is not empty. But if you ask me what that n is, who knows? We are working abstractly. We don't have anything. And that's the good point. It means that you are making something out of mainly nothing. Is that clear? Okay, so this is not empty. Yes? Why I insisted you to show that it is not empty? Does it remind you about something? What is one very important principle regarding natural numbers? Probably you have studied. Have you heard about well-ordering principle? Okay, you should. Okay, but well-ordering principle, it means that if you have a subset of the natural numbers which is not empty, it has a minimum. Intuitively, it is very clear. If you take a subset from the natural numbers which is not empty, there is one of them which is the smallest one. Okay? That's one of the, so this is well-ordering principle. So this means that by well-ordering principle, so by well-ordering principle, there is a minimum for it. A has a minimum. So let M naught be equal to the minimum of A. Yes? So the existence of minimum should be proven first. So M naught is this one. Okay? So what does it mean? Let me write it. Therefore, it is guaranteed that M naught, because M naught is the minimum of this set, so this means M naught is in A. So it means that not only I know M naught is a natural number, but I also know that M naught belongs to H. Yes, because all the elements from here satisfy these two properties, including the smallest. Is that right? Okay, now clay. I want you to fill it up. I hope that you haven't forgotten. So do you remember what I told you here? I told you that you write A to power, A is here. If it is already there, you are done. If A1, A2 might be here or not. The first time that A to some power enters into H, I want to show that that plays the role of the generator. Okay, so Clay, can you fill it up? Yes?
H is equal to
Yes?
A to the power M0.
Correct. That's what we want to show. Because do you agree that if I can prove this claim, I am done? Do you see that H becomes cyclic? Yes? So prove that, now prove of the claim. Proof of the claim. Okay, so you know that. How should I prove the equality? Again, you shouldn't think here, because that's not the hard part. If I want to prove this, I have to prove two things. Yes? So let me put this in a pair of brackets. So that is what we want to prove. So which one is clear and which one we have to prove? So how should I prove this? This one is hopefully simple, yes? Do you see that? So let me write this number 1. Let me write this number 2. So number 1 is easy. I want to prove that this is the case. Let me go a little bit faster. So if I again the same technique, I will take something here, yes? And then can you tell me what is the meaning? So you should be quick in these things. These are not, you don't have to be creative here. It means what? There exists, so let me use different letters, S in Z, such that X is equal to M naught to power S. Yes? But why this belongs to H? Yes?
Because the base belongs to H.
Yes, because A to the power of M naught belongs to H. H is a subgroup, yes? So this belongs to H. Yes?
Should we exclude 0 from, so S cannot be 0 still? Because we don't include the identity from before? Or?
No.
Okay, we do it. Oh, you're right, yeah.
Oh,
sorry.
because H has to have
Yeah,
E
yeah,
itself.
no,
So this is definitely in H. Yes, I'm not explaining it too much because A to the power of M naught is 8 in H, and H is a subgroup, so it is closed on the binary operation. So I raise it to power S, which is an integer, it becomes an H. So this one is done. Okay, so number 2, I want to prove number 2. How should I prove number 2? Again, the technique is clear. What should I do? This time I take x here and I want to prove it is there. Yes? So I want to show that, so if x is in H, I want to show that x is also there. Well, is that right? So tell me, how should I continue? Let me give you the first step. H is a subset of G. So x belongs to H, so it means x belongs to G. Yes? But G is cyclic. So this means that there exists a T in Z such that x is equal to a to power T. Do you agree? But now, be careful, don't lose what you are going to do. You took an x in H, this is a standard trick. I was able to come up to this point, but that is not useful. Because I want to show x is here, I have to show that x is the power of a to the m naught, m0. Is that right? I wasn't able to do that. I was able to show that x is a power of a, which is more obvious from the very beginning. But I want now to show it is a power, an integer power of a to the power of m0. So what do you think I should do? Yes?
Prove that every t can be described as m in the original in A.
As a power of m,
Yes.
m naught.
Yes, exactly.
Yes? Okay. And it means that t is divisible by m naught.
Yeah.
We had a very standard trick now. Division algorithm. Yes? So you see that this is repeating itself over and over again. So I would say that t belongs to z, yes, and m naught belongs to n up there. So by division algorithm, I can conclude the existence. There are a lot of letters. I don't want to. So there exists a q. I have already used in this problem or not? No, I haven't used q. Was for the okay. So I would say that q and r in z such that t is equal to m naught q plus r. But the most important part, r is what t is equal to m naught q plus r, but r is between and m naught minus 1. Yes? Again, you hopefully you know the technique. If r is 0, I am done, because if r is 0, I reach the goal. T becomes m naught q. Do you agree? If r is not 1, so if we prove that r is equal to 0, if not, r is between 1 and n naught minus 1. Yes? R is between 1 and m naught minus 1. Okay, therefore, a to power t becomes what? Becomes a to power m naught q plus r. Do you agree? And then, do you know how should I continue?
You write it as a to the power of mq times a to the power of r,
Yes, and then
and then the first one becomes e.
no e this time. Everything is not similar as before. It's not e. I don't know, but I know something. Okay, let me do it. Let me do this one. Can you tell me what is a r from here? Don't look inside. This one and this one. I want you to immediately tell me what is a to the power of r. You multiply everything, for example, from the left by the inverse of this guy. Is that right? So I will say that it is a to power m naught to power minus q to the power a to the power of t. Do you agree with this one or not? I just multiply, so forget about the middle one. I multiplied the left from the left by the inverse of this one. The inverse of this one, it means it is negative. Do you see that? Yes or no? Okay. But now, what is the contradiction? The problem is finished. What is the contradiction? Because do you remember, I need a contradiction. Because I am assuming that I want to show R is 0. If you don't believe in me, you have to believe in this, and then you will see that you are in trouble. Okay, so why is contradiction? Yes, please.
Because we know that m naught times minus q times t is greater than m minus 1.
No. But that's not a contradiction.
No, that's true.
So it's not wrong, but it's not a contradiction. But let me ask you, where this is coming from? This belongs to where? No. It's all, everything is in G. That's not a surprise. X is equal to a to power t. X was chosen from H. Yes? So this one is in H. Do you see that? X is in H, then I realized X is in this form. So this X is in H. So it means a to power t is in H. Do you see that? Where is this?
Also in A.
In H. Why? Because a to the m naught is in H. H is a subgroup, so it is closed under raising to powers, integer powers. So this is also in H. So the totality will be where? Where will be this multiplied by that?
H.
In H, because H is closed. But that's contradiction. Do you see why? So this means therefore, a to power r belongs to H. And I would write contradiction. Do you feel why it's contradiction? Yes?
A to the power 0 is not an H.
No, this is a to power r. A to power 0, by the way, you are confused. A to power 0 is definitely in H. Because if I ask you what is a to power 0, what do you say? E. If you have a subgroup, it should contain the identity. Otherwise, it is not a group in itself, yes? The reason I separated them, I didn't say that. I am saying that if H is only E, the problem is finished. It is already cyclic. So I am assuming that it has something more than E to it. E is already there. But why is contradiction? It's a very beautiful. I mean, this is the character of abstract algebra. Yes. Doesn't matter. Yes.
Because if m naught is the smallest,
You see, because what was m naught? M naught was the minimum, was the first time a to some power goes into H. But a to power t is a to power r is also in H. But what is r? R is less than m naught minus 1. So you have to live with the contradiction. On the one hand, m naught is the minimum is the minimum natural number for which a to power that number goes into H, but you will also find a smaller one. So on the one hand, m naught is the smallest one. On the other hand, you find something smaller so that a to r goes into H. So you cannot live with this contradiction. Of course, many people do. People are living in contradictions all the time, but mathematics will collapse. So this is why I don't know how we should cover, but I have to go very fast now. I hope that you understood what is going on. So this is one of the theorems, the first type of theorems that you are learning abstract algebra. And this is in the beginning might be hard, but this is the way, okay? And the way, let me pause. Okay, any questions? Okay. So let us have the break here. Yeah, let us do this one as well. Okay, subgroups of size. So from now on, what you learn is that, first of all, tell me, are you feeling somehow understand? I mean, you have to go and repeat it if you want to, or watch the video again. to digest, but hopefully the picture is more or less clear. And that is very important. It's extremely beautiful. I hope that you feel it as I am excited now, okay? Because we started with more or less nothing. Yes, we have a group G, which don't know anything about that G. We only know something about it. We know it is cyclic, and we don't even know the generator of it. But we are claiming that no matter how subgroup you choose, which subgroup you choose from it, it is also cyclic. Okay? And if, for me, to be able to reproduce this proof, I've seen it long back. Okay? The only thing that I remember here was the idea of the generator of H. Because if I want to prove that H is cyclic, I know something. I have to present a generator. And because nothing is given in my hand, the only hope that I have is to use the generator of the original set, original group, to construct a generator for my subgroup. And I give it energy and energy. I didn't give it, mathematicians did it. And then finally they solved the problem. Okay, so that's the idea. Okay, so now let us see what we can do for the next one. And so it might be you have a little bit more experience now. Theorem 2, if G is a cyclic group of order n, can you see it here? And if H is a subgroup of G, then the order of H divides n. Okay? So this we can do quickly, it's not hard. This is a special case of a very important theorem that hopefully we will learn later, and that is called Lagrange theorem. So what is Lagrange theorem? It is telling you that if you have a finite group, finite, and if you have a subgroup of that finite group, the order of subgroup always divides the order of the group. You don't need to worry about this one, that this is the most general theorem that we have regarding the orders of a group and a subgroup for a finite case. So if we have already proven this, then we are done. Okay? Because this is a special case of this more important theorem. Okay? But now what we want to do is to prove this only for this case. So this comes later. So, but in this problem, we have G. We know that G is in this theorem. Sorry, this is Theorem 2, Part 1. Okay, so Theorem 2, Part 1. Yes, the first part. We know that this is the case, and we know that is a subgroup, cyclic group of order n. So, and we know that order of G is n. Okay, and then we know that H is a subgroup of G. I want to prove what? I want to prove that order of H divides n. This is what I want to show. Yes? Do you agree? Okay, but now when you see this, you already know that this group is cyclic, and you see this, it means that this is a subgroup of your cyclic group. Just now we showed that because this is a subgroup of a cyclic group, it is itself cyclic. And you also know the generator. So from the previous theorem, so Theorem 1 tells me, so proof. Theorem 1 tells me that the order of H is what? Tells me that H, by the notation in the proof, is a to the power of m naught. Yes? We just proved this. Okay? And now I want to say something about the order of H. So you see, Theorem 1 grants this for me. It's still on the board. And now I want to use this to prove this last part. So what do you think I will do first? Tell me. What do you think the first try will be? This is what, in my hand, my goal is to prove this relation between two numbers, order of H and n, order of G. What do you think I will do first? It is not on the board. It is something. So no, I mean the first step is just a mathematical way of thinking. What do you think is a good way to do to continue? You want to say something about order of h. Isn't it natural to say that okay, if this is equal to this, so the order of h will be equal to the order of this? I mean, for me, it's not that very hard to take this step. Because I know this, I want to know something about the order. If these two subgroups are the same, the orders will also be the same. But do you remember something yesterday? Do you remember I wrote order of this is equal to what? We had it before for the finite case. Even if for the infinite case. Here I have a finite case. So order of this, do you remember in the finite case? So you see, memory is extremely important. So do you remember for the finite case, it was a to power 2 up to a to power n minus 1. Do you remember this? So then we had the order of this is n, which is equal to the order of a. Okay? But now can you tell me what can I write for this one? This is something we had yesterday. I want to use it now. Yes?
It's the order of a to the power m0, which is just m0.
So that is something I want you to understand. Yes, in a matter of seconds you should be able to write that because I want you to interpret this in this way in your head. Not just A. It is telling you that the order of this subgroup, whatever the generator is equal to the order of the generator. But here the generator is a to the power of m naught. I don't know if I say not, I don't know why Americans, not is this word. Okay, I don't know why, but this is the correct word. Okay, so a to the power of m naught. So it means that I have to go, tell me, what should I write? I will write, I want you to fill it up. A to the power m naught. Yes? But then how should I continue? Yes?
That's m0, is it?
No. We had a big theorem yesterday. It was equal to order of A divided by GCD of order of A and then m naught. This was a theorem we had just yesterday. Do you remember? And what is order of A in this problem? Order of A is n. Because the order of G is said to be n, and order of this and order of A are the same. So order of A is equal to the order of G, which is n, and this is GCD of n and n naught. Do you agree? Okay, just 1 minute and we have the break. You are supposed to finish it. Are you? What was my goal? Don't forget. Your goal is this one. What I did, I calculated OH for you. OH is this number. I don't know any of these numbers. I don't know n, I don't know m naught. But I want to say something. I want to make sure, I want to prove for you that this number divides n. Yes?
The GCD of n and m naught has to be a divisor of n
Yes.
because it's the greatest.
Finished.
Yeah.
Yes. So this divides n. Do you see that? Because this is a greatest divisor for n, between n and m naught. So n divided by this is definitely a number of n divisible by. So finished. Is that right? Okay, so let us have a break now. Thank you.